Okay, I'll start by. Okay, now, so till this, I must have sent you PPTs up to this point. So these were what did we do? What we have seen so far. We introduced random variables of the discrete and the continuous type, and we saw other probability concepts attached to them, and we introduced the distribution, discrete distributions and continuous distributions. There we saw normal distribution mostly, and we also introduced gamma distribution also. We'll see more of the gamma distribution in this class because the discussion is going to end with chi-square. So we'll see some more of gamma distributions in the gamma function also now in this class. So after distribution, the binomial distribution also we discussed, and we discussed in some sketchy detail the Poisson and the exponential Poisson distribution also. Other continuous distributions like exponential distributions and all we saw. And after that, we introduced functions of random variables, both in the discrete case and the continuous case. Functions of one random variable and functions of two random variables, and the functions of normal random variables. I don't know whether I've done that. Functions of normal random variables for one or two. Now let's discuss this class. Let's start this class. This, for example, this linear function of two random variables. This was the example that we saw. We'll see extended to the case of several random variables. And in this class, what are we going to see? Several random variables.
Sir.
Yeah, who is this?
Sir, we can't see your PPT.
Can you? You can't see your PPT? Nobody can see
Sir,
the
No, sir, I can.
Sir, I can.
Sir, we can.
Drishan, you have to probably rejoin.
Okay, sir.
Now can you?
Yeah, okay. Now I can. Thank you, sir.
So, so these, I'll give you some very simple examples of so far when we have been, I don't know whether by design or by oversight, I concentrated more on the continuous random variables, the functions of continuous random variables. Let me give you some very simple examples of functions of discrete random variables. Functions of normal random variables, which will again bring us back to standard normal random variables and the chi-square, the gamma distribution, the chi-square distribution. This is where we are going to go today. I hope you're all aware that for the test, whatever we finish today, the portions will be up to whatever we finish today. Okay?
Yes, sir.
And I hope you have been receiving all my PPTs. And I plan to send you some review questions. But review questions, I won't have time to type it in. Is it okay if I write it and send it to you, scan it and send it to you?
Yes, sir.
Yes. I hope you understand my handwriting. That's my only hassle. But okay, that's what it's going to happen. I'll do it over the weekend. Now, let us consider outcomes in several random experiments or one random experiment several times. This is a question that actually bothers people actually. Hello? 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 Okay. Now, what is it now? Outcomes from several random experiments or one random experiment conducted several times in which each trial results in one measurement. So that can be considered a random variable. Okay, this is what exactly is what we're going to see. What do you mean by a sample of size 2, 10, a sample of size n? Okay, so we obtain collection of several random variables from several experiments. Suppose these experiments are performed in such a way that the events associated with any one of them are independent of the events associated with others, and hence the corresponding random variables are independent in a probabilistic sense. What do you mean by that? Recall that if the two random variables, x1 and x2, of the discrete type with probability mass function respectively, and we have seen this before, then they seem to be independent, the joint PMF can be written fx1, f2, x2. Sometimes two random experiments are exactly the same. What do you mean by that? By rolling a fair die twice, resulting first in x1 and then x2. So it is reasonable to say that the PMF of x1 is 1 by 6, the PMF of x2 is 1 by 6. Assuming independence, it should be a fair way to perform the experiments. The joint PMF is then 1 by 36. The space of x1 and x2 is given. In general, if the PMF of independent random variables x1 and x2 is the same, then the joint PMF is fx1 and fx2. In this case, what do we mean in this case? This is what I'm saying. The random variable is nothing but rolling of a dice. This random experiment was conducted twice. The random variable is rolling a result of rolling of fair die twice. The outcome results in x1 and x2. Then we call this a random sample of size n equal to 2. So the two rolls of the fair die, we say that we have a random sample of size n is equal to 2. Same random variable, one random variable, experiment conducted twice, then the sample size of n equal to 2. From the uniform distribution. Hey, who is this? I don't know who this guy is.
So you can mute all the participants in the list.
I have muted all the participants. Don't allow attendees to unmute. See, he says don't allow attendees to unmute. You are not allowed to unmute. Okay. Okay, now this is exactly example. Go through it. It's quite simple actually. x1, x2 be two independent random variables resulting in from two rows of a fair die. That's it. Sample size of 2 here. Distribution with PM of f of x equal to 1 by 6. Then we have expected value of x1 equal to 3.5 and variance of x1 is equal to 35 by 12. From independence, even x1, x2 is equal to 12.25, so that because the independence we can write is a product of two expectations, and the expected value, the covariance is 0 because of the independence. Suppose we define another random variable y equal to x1 plus x2. What will be the expected value of y? That will be 7 because the linear operator var y equal to 35 by 6. Remember, you get the first principles correct, then you can write the mean and the variance of any linear combinations, provided you are aware of which one is a random variable and which one is a constant. In this case, by looking at it, you can say var y is equal to var x1 plus var x2 plus covariance x1, x2. Because these two are independent, covariance x1, x2 will be 0. So you'll find only the variance and the mean. It's like this. Since the space of y is equal to 2, 3, 4 up to 12, because x1 plus x2, we have this g2 is equal to 1 by 36, g3 is equal to 1 by 18, and so on. suppose we make a list of all these PMFs, you'll get like this. The results in the PMF are given by for Y. It's very easy to calculate expected value of Y and the variance of Y, which agrees with the answers obtained earlier. That is it now. This is expected value of Y is equal to 7 and 35 by 6. Can also be calculated from the PMF.
Sir, in the variance of y,
Yeah.
y is written 12 times y minus 7 square.
Variance of Y.
I
This
think
is
it's next slide, sir.
next slide.
Yes, sir. After
Where is
this,
the variance?
here,
Yeah.
sir, variance y, and it's 12 into y minus 7 square.
Yeah. Okay. This 12 should go up actually.
It's summation only, right? Okay.
The upper limit of summation. That's a typing mistake. Okay. First one. Okay. So in typing tech, this y is equal to 2 is underscore, and that should be the, what is it? This sign, the upper scale of 6. I forgot to do that. So it should be the upper limit of summation. Is it okay? 33 by 6. All the notions about two independent variables can be extended to n independent variables, which can be thought of as measurements on the outcomes of n random experiments. Okay, now random experiment on the same independent variable. X1 is the first random experiment, X2 is the second, Xn are the nth, is the nth. They are independent. Joint PMF of PDF is a product of the respective PMFs. So when somebody says that I have a random sample of size n, X1 to Xn, this is only one random variable, experiment conducted n times. Okay, this is exactly the idea. What do you mean by a random sample? This is the idea of a random sample of size n from that common distribution. If n of all n of the distributions are the same, then we can add that they are n independent and identically distributed random variables, the so-called IID assumption that we are going to use so heavily in econometrics. So we release first we'll start with IID. We relax the independent assumptions and allow for autocorrelations. Autocorrelations are invariably the feature of a time series data. You don't get autocorrelations in cross-section data. You do get autocorrelations in cross-section data. They are called spatial autocorrelations. In time series, autocorrelations are called temporal autocorrelations. And temporal correlations are called autocorrelations. And you relax the identically distributed random variables. You enter into what is called heteroscedasticity. For long, it was thought time series correlation was a problem of time series data, and heteroscedasticity that of cross-section data. Now you know heteroscedasticity is very much a part of time series data, resulting in the so-called arch-gauge models. So that's what. So this IID, which in econometrics, we start with it and relax it one by one. If fx is a common PMF or PDF of these n random variable, joint PMF or PDF is this a product of the respective PMFs or PDFs. Oh, the mathematical expectation. Please go through it. There's nothing for me to explain in the discrete case. It's a function of x2, x2 is given by this. We shall next show that the expected value of the product of functions of n independent random variables is the product of their expected values. Then x is ey is equal to this. It can be written this way. We shall show it for the discrete case as follows. This is the so-called proof forgetting. For the continuous case, we have to make the obvious shift from summation to integrals. Note that mu y is equal to expected value of ei xi. Summation take ei out, so expectation xl ei mu I, because the expected value of the sum of the expected value, sigma square y is given by this. I hope there's no mistake in this. No, xi minus mu I whole square, yeah. Okay, yeah, aj because of the cross products. Case illustrates how to obtain the mean and variance of a linear function of independent variables, but it can be easily modified to the case if xi and xj are correlated. This is it. The mean is still the same. What is this statement tell you? Ai aj rho ij sigma sig j equal to aj ai rho ji sigma j sigma I.
So that it's like symmetric in the sense
Yeah,
that
the off diagonal. Can you see the off diagonal elements?
yeah, they're the same.
They are the mean because it's symmetric matrix, right? The mean of y is still the same in both the cases, namely mu y is equal to a, but the variance. Two simple examples will explain how to use the above results. Okay, now let's look at this. The independent variables x1 and x2 have respective means. mu1 equal to -4, variance of sigma square is equal to sigma 2 square. Then the mean and variance of y is equal to, very simple.
Sir. So can you please move last slide?
This is the last slide. Which one?
Before this one.
This one?
Yes, sir. What is the significance of I and J here?
What is the?
What is the interpretation of I J, or how we equate both the equation?
This one?
Yes, sir. Moreover, AI, AJ, rho, IJ, sigma.
Just now I asked this question and somebody answered. What is this? This is a product of, the covariances are symmetric, remember? This product will be equal to this product. Covariances are always symmetric. Rho ij is nothing but rho j. What is rho ij? xi minus mu I, xi minus, that's what I have given, is it? Expectation rules. So rho ji will be the other one, the covariance of xj, mu j, xi mu I by standard deviation of I and j, isn't it? So the product will be the same for both the denominator and the numerator for both the cases, and hence is equality. Can we proceed?
Yes, sir, yes. Thank you.
This is it now. Now, what am I going to next now? Example 2, let x1, x2 be a random variable from a distribution of the mean mu and variance sigma square. Y is equal to x1 minus x2, mu equal to 0, sigma square, y is equal to 2 sigma square. Now consider the mean of a random sample. X1, x2 from a distribution of the mean mu and variance sigma square. Which is a linear function with ai equal to 1 by n. Oh, I'm talking about this linear function. This is the linear function I was talking of. Okay. So this linear function of ai is equal to 1 by n. Then mu x bar equal to summation equal to mu and sigma square x bar equal to sigma square by n. That is, the mean of x bar is the distribution from which the sample arose, but the variance of x bar is the underlying distribution divided by n. Any function of the sample observations x1, x2 that does not have any unknown parameter is called a statistic. What is called a statistic? This is the definition of a statistic. Any function of the sample observations that does not have any unknown parameters is called a statistic. So statistic must be defined completely in terms of observed values and known variables. For example, the wireless estimator beta hat estimate is nothing but x transpose x inverse x transpose y. That is a statistic that has been explained completely in terms of known values. Okay. Similarly for sigma square and all those things. Then it is called a statistic. So here x bar is a statistic and also an estimator of the distribution mean mu. So x bar is now calculated in terms of given sample values. Mu is unknown. This is actually mu. It should be this way only. Mu is unknown variable. An estimator of mu is nothing but x bar, and the resulting estimate is some sort of a sample value, sample equivalent of the unknown parameter mu. Okay, all these things will refine in econometrics. We'll come back to this in econometrics, estimate, and all those stuff. Another important statistic is the sample variance. Oh, this we'll spend quite some time in econometrics to show that the so-called S square is an unbiased estimator, efficient estimator, consistent estimator, all those stuff. Don't worry, I'll bombard you with all those stuff. Notes is ready. Okay, the sample variance. We'll show this, use this, because I need an estimator for sigma square. So we'll use this. See, S square is a statistic known is completely explained in terms of known values. Okay, now this gets interesting. Get ready to do some work. Random functions associated with normal distributions. In statistical applications, it is often assumed that the population from which a sample is taken is normally distributed. Interest centers around estimating the parameters mu and sigma square, or in testing hypotheses about these parameters. Yeah, as we have seen, the usual statistics that are used as estimated the sample mean x bar and the sample variance a square. We need to know something about the distribution of these statistics to pass. Remember, for any statistical inference, x bar is a statistic, I need a distribution. S square is a statistic, I need a distribution. So which one? Then only we can test hypothesis about x bar. Suppose you want to say x bar is equal to 20. That is a null hypothesis, and we have an alternative hypothesis, and x bar is less than 20. And this is the so-called one-sided test. Suppose we have null is equal to x bar is equal to 20, alternate x bar is not equal to 20. This is a two-sided test. We'll see in all these things in inference. So to do all these things, we need to know the distribution of these statistics. So we shall use the moment generating function to show the result. Recall that the moment generating function once found uniquely determines the distribution of random variable and their consideration. Before proceeding, we shall demonstrate some results involving the MGF. Recall some of our earlier results on MGF. The following results are a continuation of results involving MGF. Go through it. AIT is very important. Remember, that's what we discussed in the stock prices also. The stock price A was 1, if I remember right. Given the independence of x, we'll show this how. Okay, given the independence of x, is the MGF of y is given by this. So the third line tells you the independence property, the third equality. So any individual expected moment is mx is this. So thus we have the product. Okay. Corollary follows immediately if x1, x2 are observations of a random sample from a distribution with the moment generating function mt. Where is this? The moment generating function of y is this. The moment generating function of x bar is this. You never know when you may need all this stuff, so I don't know whether I'm going to prove all this stuff. No, I'm not going to prove, so please take it down. I don't know whether you may need it somewhere down the line.
Excuse me, sir. Sir? Sir?
Yep. Who is this?
Sir, Swarupjit here.
Yeah.
Yeah, sir, in the moment generating function of x bar, right? So that is pi running from 1 to n, tn, that is combination.
Combination matlab?
So tcn, or what is that in the bracket? That is tn.
Yeah. This follows from here, isn't it? And the one that is above it, that's above.
Yes, sir. That this notation, that t and below there is n.
Oh no, the same n, I think.
No, sir. I'm not getting the fact that when we write it like this, that means combination, right? T and n. If we write it like that way
Yeah,
in the bracket,
yeah,
so it becomes tcn.
yeah, yes.
That is that, right?
Yeah. A
Oh,
corollary
okay.
follows
No,
from here. Corollary,
no,
corollary,
sir, it's
corollary
T
follows from here. What is this?
N.
So it is T by N, right?
It is
T
He is
by
saying
n.
about combination.
That is t by n.
Yes, yes.
Yes, it's not combination and combination.
Oh, okay.
What is the question here? Is there a mistake here?
No, sir, it's okay.
No, sir.
No, sir.
Okay. Can we go to the next slide?
Yes,
sir.
sir.
We can now use the MGF technique, descriptive proof theorem, that deals with the linear functions of independent, normally distributed variables. What is this? Oh no, another boring stuff. If x1, x2, xn are mutually independent normal variables with mean, mu1, mu2, and variance is sigma 1, sigma squared respectively, then the linear function has a normal distribution. Can somebody prove this? So boring. Where is variables?
So from the uniqueness of MGF, this can be derived.
Should you show? Should I show it? Okay. From a result above, we have with. Can we show this now? Is it okay? This is standard stuff. Only thing you have to write, you have to have the patience to write it out. That's the only thing. I have shown the patience to at least to type it out. Nothing big here.
Sir, can we also use the result that a linear, like a linear equation, like the linear combination of normal variables is also normal? So
Yeah,
finding
yes, yeah,
extinction and
yes. Okay, and here. It follows that A1 S is okay. I'm slowly going there to. This is the MGF of a distribution. That is, this is the MGF of a distribution. That is, see the point. Given the MGF, you write the distribution. You write, given the distribution, you bring the MGF. This is also a good exercise. Be ready for such exercise. Look at the question. So why has this normal distribution? It can also be shown because MGF uniquely describes random variables distribution. So you also be ready for such questions, simple questions, okay? So given this distribution, right, the MGF of a distribution, this is, why has this normal distribution? It can also be shown that the difference of two independent normally distributed random variables has a normal distribution. Okay, take it as an exercise and show through MGF. Take it as an exercise and show through the MGF that Y is normally distributed with mean mu1 minus mu2, sigma 1 square, sigma 2 square. The moment, see, you should develop, after once or twice, you will develop the ability to say the variance and mean of any combination of random variables, so long as you remember what is a random variable, which is a random variable in the constants, if any. By looking at it, you can say it's equal to mu1 minus mu2 and variance sigma 1 square, sigma 2 square, because they are two independent, the covariance vanishes. But it's a good exercise to show it through the MGF. Take it as a homework. I'm going to give you another homework, which is a pretty tough one, because the integral is difficult to evaluate. It comes later. Okay, look at this. What should be the null hypothesis? Okay, you go through this. I'll ask you a simple question on null hypothesis. Oh, I have given the answer. This is a simple econometric. Suppose you want to test this, probability x1 is greater than x2. We shall find the probability that the fat produced from x1 exceeds that produced by x2. So we are forming the linear random variable here, another random variable y x1 minus x2. Then the distribution of y is here. You can easily find it from the previous result. So the p1 x2 is equal to py greater than 0 is this. Suppose what should be the null hypothesis if the x1 and x2 produce only the same fat? What will be the null hypothesis? Then y should be
Equal.
zero. So this is what. But given this probability, I think it's quite good probability. So later on we'll take it up and see how to test. Suppose I get 0.006179. How to test whether this can be treated as zero. So that is the part of the hypothesis testing. So this is how you proceed. This is simple stuff now. X1 and X2 are observations of random sample of size n from normal distribution. Then the distribution of the sample mean, the mu and sigma square. I think we have seen this before. To prove this, okay. The above test results show that if x1, x2 is a random sample from the normal distribution, but the variance sigma square n, the means that x bar, this means that x bar, okay, what does that mean? Why am I showing it again? Okay, this means that x bar has a greater probability of falling into an interval containing mu than that's a single observation. What is the essence of this in one sentence? You go through it. What is the essence? There is a essence. There is a point. There is an essence. What am I driving at?
So x bar is an approximate of the mu.
Sorry?
So the x bar is a proper approximate of the mu. So the estimating.
Oh, no, that's not what I'm saying. Concentrate on x bar and x1. You see the probability of x bar and see the probability of x1. What is the difference? What makes the probability so high in x bar?
X bar's range
the
is
spread has reduced.
You are getting no. This is simple property that I'm driving it, which is so standard in statistics and econometrics.
As we increase
Central
n,
probability theorem.
What is this? Concentrate. X bar. What is the sample size of x bar? X bar is calculated from how many observations?
64.
64. I given you the answer right before. X bar has a greater probability of falling into an interval containing mu than there's a single observation x1. Okay, so this highlights the importance of two things. Should concentrate on x bar. Not only that, this highlights the role of sample size. Okay, we'll see later what in econometrics, in statistics, you must have been taught that a large sample size is 30. Okay, you'll see later the three examples that I'm going to tell you. So the central limit theorem tells you that, sorry?
Sir, what Adrish said is the similar thing, right? I mean, he also said that since x bar is approximation of mean of the entire of the random sample, so it should lie in that interval with a greater probability than x1.
He was more statistics in his answer. I was more, I wanted a pedestrian explanation. Can you say that? The pedestrian explanation is about the sample size. That's it. Okay. The importance of sample size. Okay, so that's it. So in statistics, you say n is greater than 30. In classical statistics, is supposed to be a large sample, n greater than 30. And it has been shown later that if your original sample is from normal distribution, original true sample, true distribution is a normal distribution, a sample of 2 or 3 is sufficient. That's been shown. That can be shown also. If second point, if the underlying true distribution is not normal but a symmetric distribution, then you need n equal to 30. The third point, the underlying distribution is neither symmetric nor true distribution is not normal, then you'll be surprised to see, find later on, I think I have a picture on that, you need at least n is equal to 100 to say something about, to use the central limit theorem and say no matter what my underlying distribution is, it will go to normal distribution. So n equal to greater than 30 has a small a caveat. Okay, the original distribution is at least symmetric, about which also we do not know. Okay, so these are the 3 points. I think I have a picture later on which will show this. For now, the property is illustrated in the next example. If let x1, x2 be a random sample from the n 50, 16 distribution, we know that the distribution of x bar is 50 and 16 by n. To illustrate the effect of n, refer to the next figure.
Sir, are the x1, x2, xn individual samples or are they elements of the sample?
x1, x2. This is exactly what I said. Xn, xt be a random sample from, it's a sample size of n, the same random variable, n experiments have been conducted. Okay. Hello.
Yes, sir. Yes.
This is sample size of n for one random variable only, conducted n experiments, n time experiments conducted n times. The first time x1, second time x2, the nth time xn. This is called a random sample of size n.
Hello, sir.
Yes.
Sir, could you explain that once more why x bar has greater probability than x1 in being in the interval containing mu?
This means that x bar has a greater probability of falling into an interval containing mu than does a single observation, say x1, isn't it? X bar, see, what is the value of x bar here is equal to mu 50. Okay, this is such common sense. What is the probability that x1 will be 50 when I consider only 2 random observations? And what is the same probability when I'm considering n observations? Does this picture tell you anything? As the sample size increases, what is happening to the distribution? What is happening to the PDF?
It's becoming more concentrated around the mean.
So it becomes leptokurtic.
Yes.
Consistency.
What is that? Can you see as the sample size increases, the PDF is getting more and more concentrated around the value 50. When n is equal to 64, compare the area. Compare the areas that represent probability that x bar is between 49 and 51 and 49. Compare the areas that represent p is equal to 49 x bar 51. Hello, somebody asked this question. Who was that? Can you compare the areas? The probability that x bar will be between 14 and 51, and compare the areas that x1 will be between 14 and 51. We're going to compare one observation against x bar now. Okay. The chi-square distribution in probability and statistics, an important member of the two-parameter family of continuous probability distributions, the gamma distributions and its special cases. Once a special distribution related to the gamma distribution is the chi-square distribution. The special gamma distributions arise as sampling distributions of variance estimators based on random samples from a normal distribution, because we use chi-square distribution to evaluate or to pass conclusions on the variance of estimators based on random samples arising from a normal distribution. Understand this word, normal distribution. But we shall discuss the gamma distribution first. So this is a distribution that I've seen before. It's a popular distribution for random variables that take only positive values. In economics, it is often used to model income distribution. It's often used to normal income distribution along with other distributions called log normal distribution. We'll see that also later. We shall state next some results involving gamma distribution. Before determining the characteristics of a gamma distribution, we shall state the gamma function. It is defined by this. This integral is positive for 0 less than t. The values of it are given in tables of integrals always. We take this down, the gamma function. Next, we'll define the gamma distribution. Take this down also. You may need it for the later exercises. To check if fx is a PDF, note that. Okay, check if fx is a PDF. Show that it is a PDF.
Yes, sir. It is a PDF.
This is the proof.
Yes, sir.
Can I go back? Oh, I missed this slide. Just hold on a minute. Okay, before we proceed, I missed this slide. Can you understand this example? Before we proceed with the gamma distribution, I missed this slide, and I also missed a homework that I wanted to give you. Can you go to the slide? I'm sorry about it. This is completely different from. I should have taken it up after this. I missed this slide. I went straight here. Okay. Let x1, x2, x3 be a random sample from a distribution with PDF fx is equal to e power minus x. If you can recall, this is called the standard exponential distribution with a parameter equal to 1. If the underlying parameter beta that becomes 1, this becomes the standard exponential distribution. The joint PDF of these three random variables is this.
Sir, x1, x2, x3 are independent.
Yes. Because that's what I is given here.
It's given a random sample, so it is independent.
Yeah, random sample. So the probability that P0 less than x1 is less than 1, x2 is between 2, 4, x3 between 3, 7 can be written this way, which you can calculate this way. Okay. In this type of questions, if you come up to this, that is fine for me. It's straightforward.
Yes, sir.
How about others? Hello, let me see. Let me see. Yashika? Is she there?
Yes, sir. Yeah. Yes, sir.
Do you follow this?
Yes, sir. I followed this.
Okay, let's see the other one. Who is? Oh, Adresh Majumdar. Oh, you joined late. Are you there, Adresh?
Yes, sir. No, sir. I joined only, but sir, I joined from two devices. For that, it is showing late.
No, that's okay. I mean, are you following what
Yes,
we're
sir.
doing?
Yes, sir. Yes, sir.
Okay. Okay, let me see one more person. Dheeraj, who is this? PR Dheeraj, are you there?
Present, sir.
Okay, now do you follow what you have been saying so far?
Yes, sir.
Okay. Now, can I give you a slightly difficult homework? This is because the integral is difficult to evaluate, but try. I'll give you the answer also. Take this problem. Take this problem. Okay, there is a device. Okay, it consists of three components. The device consists of three components. And if one of them fails, the device will stop working. Okay. The lifetime of the device expressed in weeks, it doesn't matter. Okay. X1, X2, X3. X1, X2, X3 of the components, the lifetime of the components X1, X2, X3 is independent. So basically X1, X2, X3 are independent. And they have the following PDF. What is it? 2x by 25 e power minus x by 5 whole square. Should I repeat?
Yes, sir. Please repeat once
Yes,
more.
sir.
Repeat the distribution.
2x by 25 e power into e power minus x by 5 whole square, minus x by 5 whole square, e power minus x by 5 whole square, x between 0 and infinity, 0 less than x less than infinity. I should have typed it, I forgot to type it.
Sir, the minus sign is outside the bracket or inside?
No,
Like
inside
minus.
e power minus x by 5 whole square, x by 5 whole square.
Okay, sir. Okay.
Okay, my question is, what is the probability that the device will stop running in the first 3 weeks? What is the probability?
X is measured in
0 to infinity.
is it days?
Weeks.
Hours? Okay, sir.
The probability that device stops running in the first 3 weeks, I think I said that before. Okay. Lifetime in weeks. What is the probability that the device stops running in the first 3 weeks? Slightly difficult sum. You should get 0.66. How will you go about it? Remember, they are independent.
Sir, either x1 is less than 3 or x2 is less than 3 or x3 is less than 3.
Yeah,
so we
how do
have
you go? Yeah.
probability of x1 union x2 union x3, and
Okay.
then we just use the inclusion exclusion principle.
Yeah, but there's a simpler way of doing it. I said that what is the probability that one of them will conquer within 3 weeks? What will be the simpler route of it?
We can
One minus probability.
Exactly, 1 minus that it will x work, isn't it? 1 minus that it will work greater than 3 weeks, more than 3 weeks. Can we do that?
Yes.
Yes, sir.
Yes, so that is an easier way of doing it. The answer should be 0.66. Okay. Okay. Now the integral could be a bit challenging. I think this is one of those Gaussian integrals or something. Okay. Can we continue with the gamma distribution? I'm sorry to once again to interrupt like this. Can we go back to gamma distribution?
Yes.
Yes.
Okay. Sorry. This is the proof that it is after all a PDF, that because it is equal to 1. Remember this gamma alpha, okay, the gamma function. Now let's take this. The MGF of a gamma distribution can be shown to be 1 by theta t alpha. The mean and the variance are mu equal to alpha theta and sigma square is equal to alpha theta square. Okay. Once we saw this, I just mentioned this as mean mu and sigma square. And after that, we went to some other distribution, and which made our life difficult. Okay, can somebody show this? Mt equal to 1 by 1 minus theta d alpha. You try, I'll show the proof immediately. It's here. The one trick that you need to do is that you rewrite it in such a way that I need a gamma alpha outside. There will be a gamma alpha in the denominator. So there should be a gamma alpha in the numerator so that these two get cancelled. After that, it's easy.
Yes, sir.
I'll just come in a minute. Okay, this is the first slide.
Sir, can you show the next slide once?
The previous to the next slide.
So the next slide.
This is the adjustment you need to do.
Yes, sir. Yes. Okay.
Yes, sir.
Yes.
Done? Done?
Yes, sir.
Yes, sir.
Okay. You founded the mean and the variance also?
Yes, sir.
Should I show or others are trying? Isn't that it?
Sir, how did we get t less than 1 by theta by the property of gamma integral.
Yeah.
Okay.
Why did we, yes sir, why did we get t less than 1 by theta?
Otherwise, it is not well defined, I think.
Yes, there is a restriction for gamma integral.
Yeah,
There.
I think it's not well defined. That much I can tell you.
Okay.
The integral is they only say it's not well defined. That's it. Okay, now what will be the moment generating function? To do that, what will be m prime t? This will be m prime t and their double prime t, so that the mean and the variance are alpha theta and alpha theta square. Okay, let's go to now. Suppose if x has a gamma distribution with theta equal to 2 and alpha equal to r by 2, where r is a positive integer, and this is one of the most important distributions in econometrics. We say that x is a chi-square distribution with r degrees of freedom, which we abbreviate and say that x is chi-square r. Okay, the table values of chi-square and how we put this and what are all the areas and applications where we'll be using chi-square is enormous. And when I come to econometrics, I'll distribute the chi-square tables and two other distributions that play a crucial role in econometrics, namely the F distribution and the T distribution. We'll see all the stuff. Normal distribution, standard normal tables, chi-square, F, and T are the principal distributions that we use in econometrics. Okay, this is the table values and everything. How to use these, we'll see later. Especially when we discuss testing of hypothesis. The mean and variance of this chi-square are respectively mu equal to alpha theta r by 2 equal to r, and theta square is equal to c. Says the mean equal to the number of degrees of freedom, and the variance equals twice the number of degrees of freedom. Okay, can somebody derive the moment generating function of a chi-square random variable? Has anybody done that? MGF of a chi-square random variable, show that it is 1 minus 2t power minus r by 2, t less than half. Again, otherwise the integral is not well defined. I don't have the proof of this. In the more general results involving the gamma distribution, we see that the MGF of a chi-square random variable 1 minus 2t equal to minus r by 2, t less than half. Okay, so if you want a proof of it, I have it in pencil. Is it okay if I scan a pencil copy and send it to you?
Yes,
So from the MGF of gamma distribution, we can just put the parameters and get the MGF.
Yeah, correct. That's all. That's what I said. From the more general results involving the gamma distribution, we see that the MGF of a chi-square random variable is this. I have derived it only from the gamma distribution only. If somebody needs the proof in detail, I have written it in pencil. Suppose I take a scanned copy and send it to you, is it okay?
Yes, sir.
I hope it is readable, it will be readable, because there's one other, two other results that I have written in pencil, but no time to type it in. Okay, now this is the CDF of a chi-square random variable. This is what is tabulated as the chi-square tables. This is what we are going to use later on. This is it, the expression for the CDF of a chi-square random variable. Let's show some important results involving chi-square random variable. X1, X2 be independent chi-square random variables with R1, R2 degrees of freedom respectively. What will be the distribution of Y, which is the sum of the X1 to Xn independent variables? It is simply chi-square and R1 plus R2 plus Rn. By theorem involving MYT with each A is equal to 1, the MGF of Y is this. That is minus Rn by 2. It has slightly gone out of the frame. This is it, which is the MGF of a chi-square R1 plus R2 Rn. That's why. That is why I wrote. That's why this result is important. On the MGF of a chi-square random variable is 1 minus 2t power minus r by 2. What will be the MGF of this MGF of n random variables is x1 r square over 2. This follows from this result. So this y is, after all, a chi-square random variable with this degrees of freedom. So this idea of commenting on the distribution given the MGF is a very important one and a very interesting one, and has been used to killing effect in statistics. But unfortunately, the moment analyzing the results through moments and finding the important moments is yet to gain ground in econometrics, because it is connected to another method of moment estimation. It somehow has not gained ground. I don't know why. We are still interested only in least squares, or many don't even do maximum likelihood, because apart from sigma square I, the whole thing is non-linear. So there are areas that you should explore further. Method of moment estimation. Another estimation which I'm not talking of in this econometrics, even though my original course outline had it, is called the Bayesian estimation, which is so important. We don't touch it. And another estimation, another method, another stream of econometrics, non-parametric. That's also I'm not touching. So that's the problem. Okay, so I hope you'll take it up. For the next two corollaries, combine the above results. Let x have a standard normal distribution, then the distribution of random variable y equal to x square has chi-square distribution with 1 degree of freedom. This also I have the proof. Okay, this also I have the proof, and then I'll take. You must have many have proved it before. Drishan, Kanika.
Sir, we had done this last day. Y equal to x square proof. In my opinion, I guess we had done this last day.
With the proof also?
Yes, sir.
Yes, sir.
We had done this.
So you don't need the proof. I'll send the proof for the general class. Okay, I'll send the proof on MGF of a chi-square random variable.
We had done this in the last class. You gave us this question in the last class. Like you had told us to derive it when we were doing.
I had given this.
Yes, sir.
Oh, I myself had given this. Okay, so okay, but I'd given this a homework probably.
No, sir. You discussed this in class when we were discussing the transformation of
But
variable.
did I give you the proof? Did I give you the proof?
Yes, sir. I suppose yes. We had done the proof.
Oh, okay. Let Z1, Z2, Zn are standard normal distributions. If these random variables are independent, and then what will happen to the sum of the squares of these random variables? They also have a distribution that is chi-square n. So this proving of all these things are all mundane, standard, routine stuff. So let me not prove all this stuff, but these results are very important, okay, which we'll use later. Calculating probabilities. Okay, that's all for. I think I'll stop for the day, and this I don't want to include it for the exam. all these things, log normal distribution and all. We will come back to this log normal distribution, other things later. People have done log normal distribution?
No, sir.
Oh, sir.
The stat students, the math students?
So we did not do this much in undergrad.
Okay.
Yes, sir. We did
So
little
it
bit.
is. So it was spending time on log normal? So these are the stuff that I intend taking later on. Stock price changes. Oh, these were seen before. We'll stop here now. With this, we'll stop. Okay.
Okay, sir.
Okay, now let's. Okay, now for the exam. Portion up to this. Is it okay?
Yes, sir.
I'll send the PPT immediately and also a scanned copy of the MGF of the chi-square random variable. The other one, mean weight, oh, sorry, exponential distribution I did not do. Okay, I've done the gamma distribution. The Poisson I did not do. Memory loss property of an exponential distribution. Oh, these things I did not do. I don't need it. You may need it for in financial econometrics, exponential distribution. Actually, you know, that was a variable distribution that I gave you. Has anyone come across this variable distribution?
Sir, I've only heard about it, but I don't know.
Okay, that's a distribution with constant rate of hazard, constant hazard rate. Every distribution has a survival function and hazard function attached to it. All these things you may need extremely in labor economics when you talk about unemployment, how a person was remained unemployed for 1 year. What is the probability that you'll get a job in the next few days, and all these things you need. Survival function, hazard function, and all these things. Every distribution has a survival function and hazard function. Okay, so all these things will be there in variable distribution, and to avoid the problems involved in variable distribution, we discuss the Berg distribution, so many other distribution. The usefulness of all these that you're learning here, you will find it only when it comes to finance. Okay, econometrics, classical econometrics, especially, is so closely around the normal distribution. Where are you going to use this variable distribution, all those stuff in finance? Okay, in time series beyond a certain point, normal distribution does not work. Okay, so this is it. So with these observations, we will stop today's lecture. It is only 10:45. That's okay.
Sir, will you give us to derive the chi-square distribution and normal distribution? Like, will you give us questions on that? To derive the distribution?
No, I may give you something and show it, whether it is a PDF or not. So those kind of questions.
So you won't give us to derive the like chi-square and normal.
No, I have not done it myself. It's so later on. I have the notes for F distribution. It is so touchy. It's this T distribution. No, don't worry. I won't ask you to derive the PDF of.
Yes, so those integrals are very, very long and.
No. As I told you, no question should take you more than 10 minutes. Is it okay?
Yes, sir.
Okay, don't go by the fact that suppose I given you 15 points. Don't think, oh, this is something should be there. This is a standard mistake done by the student. They start reading in between lines. Oh, there must be something. There's nothing. Nothing. You'll see the solution is only normally half a page. Okay, sometimes I give you 10 points for even half a page solution or 1 page solution because of the conceptual idea involved there. Understood? But I have dropped enough hints and I also given examples. I'll try to give you an idea of the questions that you may face in the review questions, that practice questions that I intend sending over the weekend. Okay, so practice question, you just practice, and wherever possible, I'll give you the answers also, but not the solution, so that you get the practice of solving it. I'll give you the answers. Is it okay?
Yes, sir.
Okay. I'll send you the PPTs immediately and yes, who is this? Paramila.
Sir, just few clarifications. So, sir, is this a 1.5 hour test?
What is that?
Sir, is this a 1.5 hour test, like
1.5
on
hours
26?
test? Yes, 1.5 hours test for 30 points.
Okay, sir, and the time for uploading is the same.
I'll send you all the instructions well before the test.
Okay, sir, and okay, practice problems have not been given out till now, right?
No, I'm
It's
not.
this weekend you're giving.
I'll
Yeah,
send it over
thank
the
you,
weekend.
sir. Thank you, sir.
Yeah, Drishan, you want to say something?
No, sir.
Okay. Okay, we shall leave. Goodbye. The class is over. Bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Bye. Bye.